Welcome to Astronomy, Chapter 11. This video is going to be the first video in the third unit of our course. Now, in the first two units, we sort of laid the foundation in Unit 1, and in the second unit, we really honed in on what's going on with the astronomy in our solar system. Now what we're going to do in our third unit is we're going to be taking another step out and now looking at the effects of what's going on to try to understand the stars. And we're going to be looking at great detail about these amazing points of light we see all throughout the sky. And there is a tremendous amount we can know about these objects by analyzing the light coming from them. And we're going to go into some pretty good detail about this. This unit is relatively short. There's only a handful of chapters. But we're going to kind of slow down a little bit on this pace and only do one a week to try to keep us in good shape. But this third part on understanding the stars starts off with how we're going to characterize the stars. And so really what we're doing here is we're trying to say, what are the traits that these stars have? Well, what is it that makes one star different from another? And turns out there's a significant amount that we know. And we'll see all the basics of how we organize these stars really into different groups based off of those traits. And we'll also do a little bit of a comparison here in terms of how these stars compare to the sun. And in fact, when we look at most of the descriptions of how we characterize stars, it's not necessarily what type is it or where is it, but a lot of times the characterization is, how is it like the sun? Is it bigger than the sun? Is it heavier than the sun? Is it hotter than the sun? Is it cooler than the sun? Almost everything of our characterization of the stars begins with our classification relative to the sun. Now, the first thing we're going to be looking at in here is this concept of parallax. Parallax is a very important idea to understand how we can determine the distance to our nearby stars. The thing that we have to remember is that the sun is very, very close to us. In astronomical terms, by comparison, the sun is very close. And then the next closest star is some 200,000 times farther away than the distance to the sun from the Earth. So we're talking about a long distance to get to these next stars. So it's not easy for us to measure those distances. Obviously, we can't directly measure. You can't put a tape measure from the Earth to the next star. It doesn't work that way. So we have to come up with some different methods. One of them is this idea we call parallax. Parallax is just a simple idea that if an object is close, we will see it moving relative to the background of stars. And so when we look at how much it moves, what we can do is we can measure in here, and they're showing you this on page 351. They're showing you this movement by measuring an angle right in here. And this angle is directly related to the distance. And so what we have here is obviously the greater the distance, the lesser the angle. So we find out that there's a relationship that effectively we can say that the distance is inversely proportional to the parallax angle. So that is a little bit about getting you started when you're going through reading parallax. And they actually give you some good calculations there on page 352. Now, the next thing you're going to be looking at is we're going to be looking at this thing we call apparent magnitude, or sometimes called apparent visual magnitude. But apparent magnitude is going to be abbreviated lowercase m. And what this is, magnitude is, if it's apparent, you just think about what that description means. It means, what does it look like? All right, so apparent magnitude means if I go outside at night and I look, how bright do the stars look? That is the apparent magnitude. And this scale was actually started by Hipparchus. And they talk about this when the ancient Greeks, Ptolemy was involved in this as well. And they talk a little bit about the history of it. But the magnitude scale is a little bit confusing. Now, I'll give you the confusing points so that hopefully it'll make more sense when you're going through doing the reading. First off, the lower the number, the brighter the object. Second thing is that you can have negative numbers. The sun, for example, is negative 27 or something of that sort. Very negative number. Obviously, the sun is the brightest looking object in the sky. The third thing that is the most confusing for a lot of people when they look at the magnitude scale for the first time is that it's nonlinear. In fact, it's based off of a logarithm. And so there's a lot of reasons why that is. And actually, we took the scale of Hipparchus from in BC times and sort of updated it to give it an actual quantifiable number. And in doing so, we found out that the relationship of how he sorted the stars out was actually logarithmic. And really, when you look at it in the sky, it kind of makes sense that you do notice the differences. But I want to point out on page 354, there is this scale that will give you some ideas. Here we see the sun being the brightest object in the sky at about negative 26. And then the moon, and Venus, and then the brightest star in our night sky is actually called Sirius. And Sirius is a star in the winter that we see. It is just actually right next to a group of stars, a very well-known group of stars. This, of course, is Orion. Orion has several bright stars in it as well. Sirius is the brightest star right behind it. And actually, Sirius may have become more famous, the name, thanks to J.K. Rowling and as the name of one of the characters, of course, in the Harry Potter books. But nonetheless, this is the brightest star in our night sky, which may be a bit perplexing because I know a lot of people have been told at some point in your life, whether or not that was correct, but a lot of people have been told that the North Star is the brightest star in the sky. It's not even close to true. In fact, the North Star is not even in the top 20. But we'll talk about the North Star is significant for other reasons, but it's not for its brightness. But nonetheless, you keep moving down the scale. Naked eye limit. If you are in a dark location, if you have good vision, and it's a clear sky, you can see maybe about a positive 6. So basically, everything that you can see at night is anywhere, star-wise, is from about a negative 1.5 to about a positive 6. That's everything that we can see. Now, obviously, if you add binoculars or telescopes, you can see much better. The best telescopes, as of the printing of this book, get to about 30th magnitude. This is very, very, very dim because this, again, this distance, the brightness is not related linearly. It is on a logarithmic scale. So that is a very, very dim object to be plus 30 magnitude. But anyways, when you're going through there, the apparent magnitude is a crucial part of understanding the stars. It is simply how the stars look. Now, the next section on absolute magnitude is if we were to take all the stars and put them at the same distance, how bright would they look? And that distance is 10 parsecs. And it gives us an idea of how they would compare. And in talking about how they compare, they show you a relationship on 356 about what we call the inverse square law. And the inverse square law simply means that the light drops off as a function of the distance squared. So the distance you are away drops off its luminosity, its brightness, more on each step. So it is a squared function. So you can see, if you were to think of this, as a circle, a circular area around the star, and where this area represented 1 square. Well, you may remember that the surface area is a function of the radius squared. So that's why we're seeing a drop-off at a squared radius, because you're talking about this squared relationship. But then they kind of put this all together here. This is an extremely well-known relationship, the distance magnitude relationship. We're not going to go into tremendous detail in this class on working with this, but it does give you an idea of how the absolute brightness is related to the apparent brightness. And there is our logarithm. There's the critter that makes it so that we have a nonlinear relationship. But this formula explains where this is coming from. All right. The second major part of this chapter is talking about the temperatures. Temperatures are very easy to tell ballpark estimates. And we talked about this way back when we talked about atomic spectra. Remember we said that, with a candle, the red part of the candle flame is hot, but the blue part is really hot. And in the same way, you can go outside on any clear night, look at the stars, and you should be able to identify color differences. That color difference is, of course, related to the temperature of those stars. And so that's what this next section is talking about, is that its surface temperature is revealed by the wavelength of light coming out of it. That's what they're going through on page 358 as well. Now, on 359, they introduce the next concept, and we're kind of bringing back in part of this foundation. Remember way back when we talked about atomic spectra, we talked about breaking the light apart, and that we can take the light coming from a star and break it into its pieces and see what something is made of. We looked at this for the sun, and we've looked at this for other things. But the idea is that the different types of light tell us what's in that star, and so their spectra ultimately end up telling us what's inside them. And so we end up giving these things a classification. And the classification sequence is a bit confusing because the order is anything but alphabetical. O, B, A, F, G, K, M is the order by surface temperature. And those are the spectral types. And they talk about the history of why they're messed up. They talk about this. They were originally from A to P, and then they've been reorganized based off of spectroscopy to O, B, A, F, G, K, M. And so there's a lot of acronyms, acrostics to help with O, B, A, F, G, K, M. One of the most well-known ones, and the way that I learned it when I first took astronomy, was, "Oh, be a fine gal, kiss me." So feel free to use that one, but I'm sure you can come up with a variety of interesting ways to organize those sequences. And they talk about, on page 360, they're talking about the different types, and they give you the color range and the temperature range for each one of those. So, and then more importantly, well, this will be the essence of what we're looking at. But then next to that, they'll also tell you what spectral lines they see, and then they even give you some examples. Now, the next section that we're going to look at is actually going to be one of the labs we're going to do. And the next section is, how do we organize all of these different types of stars? How do we sort these things out? And the answer is that about 100 years ago, in 1911, there was some work done by a couple of astronomers. One of them was the Danish astronomer Hertzsprung, and then there was another astronomer named Russell, who was working on this classification of stars based off of their spectra. And so what happened is their work was, instead of arguing with each other, they simply put their work together and formed what's known as the Hertzsprung-Russell diagram. And we will very rarely, in fact, I will probably never call it that again, because it's much easier just to call it the HR diagram. So if you hear HR diagram, it's referring to this. And here is an example of what the HR diagram looks like. Now, what this is, it is a supposedly simple graphic, and there's lots and lots of different ways you're going to see this. I think I like the version on 363 the best. Each one of those dots is a plot, a point of a star. And what they're showing you here is the different types of stars, the different classifications, not only off of their spectral type, which is ultimately simply their temperature, O, B, A, F, G, K, M, but they're also showing you their luminosity. And luminosity, remember, is just a measurement of their brightness. So the brightness is given here, magnitude is given here, temperature, and this is actually B minus V is the color, is also related to temperature. So there's a tremendous amount of information that comes from the HR diagram, and we're going to get pretty familiar with it. It is an absolute foundation of understanding the beginning of astronomy. Now, after the HR diagram, the last section in here is going to take a look at the solar masses. Now, how do we know the mass of a star? Well, if we want to know the mass of something on the Earth, if I want to know the mass of my ink pen, we take a scale and we set it on the scale or balance, and it tells me, it spits out a number. It measures how hard gravity is pulling down on it, and it calculates a number to tell me what it is. Obviously, we can't do that in space. You can't go put a bathroom scale under a star, and for a variety of reasons, it would melt, and gravity doesn't work in that direction. So we have to infer the mass of these things through non-direct means. We don't physically measure them, but we do is we measure different characteristics, and then we determine their mass indirectly. So stellar masses are found for a variety of ways, the easiest of which is in a binary system. And a binary system just means two stars that are orbiting next to each other. And what we can do is simply watch them going around, and by watching them move around, and we can calculate the center of mass, much like you can calculate the center of mass of two children on a teeter-totter. And in doing so, we can calculate the mass of each object relative to each other, and ultimately end up figuring out how massive each one is. So binary systems end up being very significant. So we can end up, and once we use a binary system to be able to measure their motion and determine their mass, then we can use that information and compare it with other stars, and then we have sort of a domino effect of once we know this, then we know this, and once we know this, then we know this. So finding how fast an object is going around ends up being a crucial part of understanding the mass of these stars. So that'll take you through the majority of what matters from the Characterizing Stars chapter. This is by far the biggest and most significant chapter in this section, in this unit. So make sure that you're keeping up with the reading. I know it gets pretty technical once we get into this third unit, but don't give up on it. Make sure you stay up with your reading. Make sure you're going through the PowerPoint, and you should be ready to get going on this homework assignment for chapter 11. Good luck.